Hi there. All right, you're ready for today. Today we're going to be talking about changes in state. Again, kind of review, but today I want you to think in terms of what's happening at a molecular level. We're going to talk about energy and the molecules, and you've never thought about it this way before. Well, maybe you have, but definitely want you to think about it that way today if you've never done it before today. All right, here we go. So our objectives. What are the energy transfers and changes of state? Okay, I want you to be able to describe that and explain the law of conservation of mass and how that relates to the states of change, changes of state, physical and chemical changes, and then the law of conservation of energy and apply that to physical changes and chemical changes. Okay, so we're going to talk about a few things today here. We're going to talk about some graphs. Okay, we're going to have a few different graphs that we've never used before, and we're going to show you some of these graphs and how these graphs are changing, are showing the change in energy. It's pretty cool. All right, so you guys have seen a table like this before, and you could probably list some things. Notice I've got some red arrows and some blue arrows, and you could list the names for gas to liquid, liquid to solid, solid to gas. Solid to gas is one that you probably have a little bit of trouble remembering. That one is called sublimation. Okay, and then if you're going the other direction, we don't have an actual blue arrow on that one, but there is another term for this. Now, I will tell you that when I was in school, they actually taught me that this way and that way was the same name. They didn't have a separate name, and I thought, that's about the stupidest thing I could ever imagine for scientists to do is come up with the same name for two exact opposite processes. I don't know if it was just a really lame textbook I had or what, but deposition is the name as you go from gas to solid, okay? What are some of these other ones, right? From a gas to a liquid. You're going to be condensing, right? Condensation. If you are going from a liquid to a gas, you are evaporating. Now, this is not quite the same as boiling. We'll talk about the differences there. From a solid to a liquid, you guys are pretty familiar with that one, right? Melting. And then from a liquid to a solid is freezing. Now, notice that the blue arrows are blue for a reason. The red arrows are red for a reason. And the reason the red arrows are what they are is because it's going to take energy to go from the various phases that you see here that are in red. And it takes, where it gives off energy if you go in the other direction. So for instance, if I freeze, that's actually a process that is giving off energy. And the ones that are red melting, that requires energy. Okay, so that's why they're red and blue, is they're telling you that one of them is actually absorbing energy, one of them is giving off energy. Okay, so here's a prettier picture of that. Okay, we've got our ice cube and our gas and our liquid. It looks up pretty good. It's basically the same thing. Again, notice that deposition isn't here. Deposition isn't going to be on your test. All right, so let's talk about these changes of state. Melting. Okay, these are the ones that require energy. Melting, evaporation, and sublimation. First of all, let's think about melting and talk about what's going on there. Energy is added to an ice cube, causing the molecules to break. Remember, this is a solid, right? So these solid particles are stuck together like this, and there's enough energy that causes it to break those bonds so that now they can move around each other. That's what I want you to start thinking about. What's actually happening at a molecular level with things like melting. Breaking those bonds, causing them to come out of their fixed position so they can slide past each other. The melting point, that's the temperature. So if you guys hear us say melting point, boiling point, things like that, these are the actual temperatures and or pressures that you'll see these processes taking place. So that's the temperature. Melting point is a temperature, and it's a characteristic property. Evaporation. Now, again, this is the liquid to gas. If I'm adding enough energy to the liquids, that now they're still able to slide across each other, right, as a liquid, but they're attracted to each other, and they are just kind of hanging out next to each other. But if I had enough energy, boom, they get apart. And they get so far apart, there's no attraction anymore, so these little particles are moving around as a gas. And so in this case, you're getting those surface molecules to move fast enough to escape. Now, when we talk about surface molecules, we're talking about the molecules that are right at the surface between the liquid and the gas. Notice that evaporation occurs at the surface, and now we're talking a little bit about boiling here. That boiling takes place under the surface. Okay, that's one of the distinctions between those two. And so you'll notice that evaporation is at any temperature, and that boiling is the particular temperature. The boiling point is going to be that temperature. But boiling is taking place when you've added enough heat to cause it to form those bubbles under the surface, where now these guys can escape and turn into a vapor. And again, so boiling is taking place under the surface. Evaporation takes place at the surface. Evaporation is taking place all the time, okay? And sublimation is taking place all the time as well. They say that things like even like a desk or something, that over millions of years that the desk will eventually sublimate. Like all those little particles disappear and it's just gone eventually. All right, so then let's talk about sublimation. Again, your solid is changing directly into a gas. And so it's got to, I mean, that's a pretty solid bond, but it escapes away, right? Mothballs, naphthalene. That's an example of sublimation. You've also got this stuff happening in your freezer. If you've ever put some ice cubes in a freezer and all of a sudden you go back, you know, month, 2 months later and the ice cubes are smaller or they're gone, that's sublimation. That's just disappeared into the filter of that, or into the system of that refrigerator. And then you've got another good example. You know, in the really cold climates, they would still put wet clothes out on the clothesline, because the wet clothes, that water would freeze, and then because of the wind and stuff, as it would sublimate, it would take away that ice, and it would take it away so that the clothes, when they brought them inside, they'd be really cold, but they would be totally dry. Wild, right? Yeah. Dry ice is another good example of sublimation, right? Solid turning directly to gas, carbon dioxide doing that. All right, let's talk about the ones where you're going to have energy being released. Freezing, condensation, and that I added that deposition in there as well, even though it's not here. Condensation, remember, particles are slowing down enough. So here you've got these gas particles and they're moving around. But if you cool it down, and remember, cooling down means slower movement. And if you get them close enough and they're able to now have a bond, now they can turn into a liquid. Now, this is what happens over particulate matter, right? You get these little particles of matter in a cloud, and you can form clouds when the liquid is forming around those little particles, and it forms from a gas, right? So freezing, these are when those particles are slowing down enough to actually form solid bonds, okay? And so that liquid is stopping and turning into a fixed position of a solid. And in deposition, that still happens, but it's going to happen really quickly. Now, in deposition, where does this happen? Well, it happens inside your closed, sealed bags inside your freezer. Have you ever had some food in the freezer? Maybe it's your vegetables or whatever. You never eat those vegetables, right? You should be, but you're not. And you pull that bag out after 3 years, and it's like caked in ice. Where'd that ice come from? It came from deposition. Okay, that stuff has slowly accumulated from the vapor, from the gas, and it turns into solid ice inside that bag. There's no way that, you know, anything else gets in there except for gas, right? So that gas is small enough it can get through, and then it turns into a solid and it slowly accumulates. Pretty cool, huh? All right, now this graph is a graph of temperature versus energy. Now, this isn't a typical phase diagram graph that we would normally show you, but I want you to take some notes of this graph because it's good for illustrating the energy gain and loss here. As my temperature is increasing, how much energy is being put into the system? Well, not a whole lot of energy gets put into the system before it gets to 0 degrees Celsius. But notice that I'm continuing to put energy into this system even though the temperature doesn't change. I'm going to show you another graph in a second that will even make this more visible. And then as I continue to increase my temperature, my energy is continuing to go up. But notice where my biggest energy changes are taking place. Like that, boom, okay, not quite 5. But this whole thing, that was barely as much. I mean, all that temperature, and it still is about the same amount of energy. So you can put a lot of energy into a system and not see it change very much, except for at the places where it actually changes state. Now, these are the places where it changes state. This is solid to liquid, and then this is liquid to gas. Look at all the energy that's required to change a liquid to a gas at 100 degrees Celsius. This is water. Tons of energy has to be put into it in order for it to change. Okay, that's what this graph is good at showing you, how much energy it takes to change that. And look, it's the same amount of energy that it takes to go the other direction. If you wanted to take it from a gas and turn it into a liquid again, you'd have to take out the same amount of energy that you put in to make it boil. Okay, all right. So Energy can be used to either increase the temperature, get those particles moving faster, or to change the state, okay, get them further apart, whether it's solid to liquid, where they're a little further apart, or liquid to gas, where they're really far apart. Standard phase diagram is going to show this transition well. I'm going to show you that here in a second. But I just want to remember, I want you to think about a solid is when your heat energy is moving those particles faster. That's just increasing the temperature. But if I transform from a solid to a liquid, my heat energy is moving them further apart, and that's going to change the state. Okay, that's from a solid to a liquid. This is just increasing them. So if I have like a piece of metal, okay, and that piece of metal is cooler, and I heat it up, now it's moving around faster. Oh, it's hot. Oh, it's hot, right? Those particles are still, they're still not moving. It's not a liquid. They're not moving around each other. They're still fixed, but now they're vibrating a little faster, okay? And so now I touch it, it's like, oh, all right, because they're vibrating so fast. And now that vibration puts itself right into my finger. My little finger molecules are like, ah, it's vibrating. Okay. All right, so then our liquid. Our liquid is when our heat energy, if I continue to add heat energy to this, my particles are going to move faster. So now my particles are still in association, but they're doing a little dance a little faster, right? Right, boom, 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 right? All right, my liquid to gas, though, man, that party has just gone out of control. They went from the rave to the, they burst out of the building. They're gone. They're not even there anymore, all right? Change of state. Gas, heat energy is moving particles faster, and it's increasing the temperature. Again, that's a gas. You can get gas really, 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 really hot, all right? So gas can be dangerous and hot, but it can get hotter and hotter and hotter, and there's no real change until you get to a plasma, okay? No change in form, but it just gets hotter and hotter. Okay, anyway, let me show you a phase diagram. This is as temperature. What the temperature is doing here on my y-axis, remember that is my dependent variable. This is my independent variable, my x-axis. This is what I'm changing. I'm basically, measuring, when am I actually taking measurements of this? What's going to happen is your phase diagram kind of looks like this. And this. What is that showing me? This is showing me, okay, like if this is below, let's say I'm at negative 10 degrees, the point at which it changes, okay, this is my temperature, and over here I'm at 0 degrees, okay, Celsius, 0 Celsius. So at this point, this is when it's changing from a solid, and now this is the phase change. This is my melting, okay? And then once I've completely changed to liquid, now my temperature can rise. So as I continue to add energy, over time, I'm continuing to heat this stuff up. It stays at 0 degrees Celsius until all of it is melted. It's really interesting. It puts all of its energy into breaking the bonds between the solids and turning them into liquids. Instead of making the liquid just go up in temperature, now you have to stir it a lot to really see this. It has to be stirred a whole lot to make sure that all those little collisions are actually going into melting the bonds, okay, or breaking the bonds between the solids and turning them into liquid. This is all just liquid, right? This is the temperature. Whoa, liquid. This is the temperature. As the temperature increases, it can go all the way up here to 100 degrees Celsius, where you're going to see it change, okay, into a gas. But this is a liquid from 0 to 100. All that energy, it's just going into making this thing warmer liquid, but it's not changing the state. And then, boom. And if I were to show you the actual amount of time, the amount of time it takes to go through and do the melting and stuff like that, that might actually be even longer, right? Boiling, it's going to take a while to boil away the entire thing of water, right? Maybe that goes way over there, right? And so this, of course, is our boiling or our evaporating, if we wanted to talk about it in terms of at the surface. But boiling is a good way to talk about this, since we're trying to probably get things going under the surface. And then it would start going up again. Now it's all a gas. Isn't that interesting? So that's a typical phase diagram. That's the way that would look. And you should be able to replicate that graph and understand how that works. Sound good? All right. Let us continue on. Oops. All right. Now, what happens if I look at it in terms of removing the energy? Well, it's going to just do the opposite, right? So if I start with my gas and I am removing energy, right? My temperature is dropping, but it's going to stop right at that 100-degree mark, because that's the temperature at which it's going to condense, go from a gas to a liquid. And then it's going to drop down. Again, so here's our liquid. And then it's going to plateau again at 0. My graph isn't exactly the same spots anymore. And then it's going to drop down once it's at 0. And then this is going to be solid. Oh my. Solid. And again, this is going to be the freezing point. Now, notice that freezing point and melting point are the same, and then the boiling point and the condensation point are going to be the same, okay? So that's the way that graph would look. Okay? Make sense? Yay! Here we go. Let's continue on. Okay. So again, freezing point is the same as melting point, all right? So this is equal to, freezing point is equal to the melting point. Temperature at which a liquid becomes a solid, same temperature at which a solid becomes a liquid, okay? Pure water's freezing point at sea level is 0 degrees Celsius. That's also going to be its melting point. All right, a lot of solids are going to freeze at temperatures higher than room temperature, right? So think about, you know, like gold. What temperature does gold freeze at? Way higher than the temperature that water freezes at, right? Pretty much anything that's a solid is a frozen state of matter, but there are some things that they don't consider freezing because, you know, you can see them change into a liquid and back into a solid, and it wasn't a temperature change that made that take place, okay? All right, so now let's talk about law of conservation of mass and law of conservation of energy. First of all, law of conservation of mass. You cannot destroy or create mass in a closed system, okay? So can't destroy or create mass in a closed system. So I want you to think about closed systems in this case. I've got my little one there. Wrong way. All right, so think about, for instance, you could change the volume of something even though you might not be changing the mass of it. So my 2 grams of ice is still going to be 2 grams of liquid water, which is going to be 2 grams of water vapor. However, that 2 grams of ice might weigh 2.1 milliliters, or have a volume of 2.1 milliliters, gets a little smaller as it turns into a liquid, 2.0 mils, and then as it turns into a water vapor, maybe it gets way bigger, right? And so, again, you might have different volumes. Does it mean that mass is not changing? No. Okay, water in an open container, that's going to evaporate, so its mass is going to change. You, on Thanksgiving, you eat all that food, your mass is changing, right? Now, it's not the same thing because you have things being inputted into different systems, from another system to another system, or vice versa, okay? All right, so the law of conservation of energy is where we talk about energy not being created or destroyed, okay? It's just changing forms. So, for instance, if I eat some food, which I'm kind of hungry right now, and I'd like to, but I'm going to have to keep talking to you guys for a little while, so just stomach, hang on. Food is chemical energy, and it's being transformed into heat energy in forms of mechanical energy. My body is moving, right? And my body temperature is beep, 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 98.6. Okay, so I've got some energy inside of me that originally started at food. So that's a transformation of energy. I'm conserving the energy. I'm just transforming it from one form to another, okay? But it doesn't get destroyed. Now, does that mean there's no way that energy can, be, like, can I not take mass and destroy or change it into energy, I should say? No, you can change mass into energy. Nuclear reactions, okay, can allow for mass and energy to be exchange. Einstein's law there, right? E equals mc squared. You guys have seen that before. So mass and energy are related to each other with respect to the speed of light squared. The idea here is that I can take mass and I can turn it into energy, and energy could be converted into mass as well, right? So yeah, that stuff can happen, but it's not going to happen in a closed system, and that's a nuclear reaction, not a chemical reaction. All right, so think about a burning candle. All right, let's burn a candle. Woo! Whoa! Fire. Wow, this thing is crazy fire. All right, there's one. Here's another one. This one could be dangerous to my finger next to it. Yeah, I think I'm going to turn that thing down. All right, candle. You may not be able to see that because of the bright lights, the big city. All right, now you've got your candle, right? All right, how will the candle's final mass compared to the initial mass? What do you think? Yeah, you're right. The candle's going to lose the mass, right? The final mass is going to be less. Does that break the law of conservation of matter? Yes or no, and why? Of course not. Why? Because it's not a closed system, right? The candle is having its wax leave, right? The wax is basically melting and then it's getting burned up into carbon dioxide and water, and it's leaving. It's going out of the system that it was in. It's going into a new system. Candle feels hot. Oh, that must mean that it's breaking the law of conservation of energy, right? No, it's just transforming, right? The chemical energy into heat energy. So a little chemical energy into heat energy, that's chemistry for you. And oh, happy birthday to you. Why did I blow out your candles? It was so rude. I'm sorry. Okay, so let's see what we learned today. Our objectives review for section 3.2. Can we describe the energy transfers in changes of state? Yeah, you now can tell me if energy was lost or required, as you go from a solid to a liquid or a liquid to a gas. Okay, be able to tell me which one requires energy and which one gives off energy. Isn't it wild to think about freezing? Freezing is actually something that's exothermic. It actually gives off energy. And we'll talk about that more at another point in the semester. But you know what they do to save the orange trees in Florida right before it's going to freeze? It's like, oh no, we got to freeze. The temperature's going to drop tonight. What are you going to do? They cover everything in, you were going to say like blankets, right? No, in water. They spray all the trees down in water. The water has energy. And as that liquid turns into a solid, it gives off that extra energy, right? Molecules of water moving fast, molecules of the ice are not moving. So it had to go from this to this. Where did this energy go? It goes into the oranges, right? And so they cover all that, all those oranges in water. And as that water freezes, it gives its energy into the oranges. Also acts as a little insulator. Isn't that cool? Isn't that wild? Hey, you can't see me anymore, can you? I was getting real dark there. Well, hi, I'm back. All right, here we go. Now, explain how the law of conservation of mass applies to changes of state. Do I, lose mass as I change state? No, I might change my volume, but I'm not going to lose my mass. Physical changes, all right? Well, I might be eating some food, but that does not violate the law of conservation of mass because it's not a closed system, right? Chemical changes, we saw our chemical changes here. Again, not a closed system. Although it's losing mass, it does not mean it's violating the law of conservation of mass. Same things with the law of conservation of energy. We have transformations, but we don't have a loss of energy. That's why it's a law. Okay, lots of fun today. We've learned about some things that are applicable, right? Even everyday things like a candle can be tied into things like melting, right? Freezing, that wax is now frozen again. And then we talked about chemical changes. In a sense, we didn't talk about the actual chemical changes, the wax turning into carbon dioxide, as much as the fact that it was not violating the law of conservation of mass or law of conservation of energy. But it's stuff that everyday observances, and there's so many other things we could talk about, so many other examples that are tied into what we learn in chemistry, which is why chemistry is awesome. All right, thank you guys. Appreciate you being here today and listening and paying attention and learning some awesome stuff that you're going to be able to apply to the rest of your life as you become amazing scientists, because science is awesome. We'll see you later. God bless you.